And in fact, when you look at a tall building, look at a giant building, Sears Tower, for instance. If you look at the Sears Tower and you see it and you think that's thousands of columns and thousands of beams, you're kind of not getting the idea. When you look at the Sears Tower, you think of it, it's one giant beam that's cantilevering out of the ground. It all works together. It's all like one system. And that's what this building is. This is a giant concrete beam that kind of cantilevers out of the ground. In fact, a lot of times when people think of cantilevers, you think like a bookshelf. I mean, this is, if you could like stick this on the wall, it would be a little heavy, but the system is there. And the system here is very similar to very conventional structural shapes. Along the corridor, we have these concrete walls that go along each of the corridors, and those act like the webs, like you might see a web on a wide flange beam. And then we have these cross walls that are like flanges, like you might be flanges on an I-beam. And at the mechanical floors, which happen roughly every 30 floors, we have these walls that tie everything together. So every piece of vertical concrete is part of this giant beam. Every piece of gravity that you have is used to resist the wind. And this is very important. It's kind of interesting. People who design water bottles or cups understand this. If you look at a cup later, you'll see it's got a ridge. It's not a flat bottom. It has a ridge around the edge. And that makes it more stable because it puts all the weight out. And if this were empty, it'd be easier to knock over than if it's full. So it's the gravity load that helps make it stable. And except right here where it's not stable at all, but okay. And so what we're trying to do is we're trying to use this gravity system to hold up the weight of the building, and you help use it to resist the wind. And we keep pushing the loads out, and I'll show you a little diagram of that later, to help make it stable, just like a full bottle or glass is more stable than the one that's empty. Now, in the very center, there's this hexagonal core, the one I talked to you about earlier, that has all the elevators. And this is absolutely essential. Okay? What it does, it keeps the building from twisting. It's like a giant axle that goes up through the building. And a very important wind researcher, Nick Isimoff, wrote a paper a few years ago where he looked at buildings that had complaints of motion. And there's a very high correlation between buildings that had complaints and buildings that had a tendency to twist in the wind. And this has a lot of effects on doors opening and closing on you, stuff like that. But also, it's kind of interesting from a visual point of view. If a building's moving back and forth, sometimes it's very difficult to notice because you have nothing to measure against, except when you have two towers next to each other and they happen to be moving out of phase. If you look at one building to the other, you might notice they're moving separately. But if you have a building that's twisting, when you sit at your desk and you look out the window past the mullion, you'll see the horizons moving on you as it rocks back and forth. And particularly a building like this, where you have these arms going out there catching the wind, that if this thing became very active in a torsional sense, in twisting mode, it could be a real problem. So this center axle is, and this is kind of one of our essential things we do in all our buildings, is we keep them from twisting. And so the center axle is able to do that.